A magnetic field can be represented by magnetic field lines, just as we did for electric field, where electric field lines represent electric field. Similar rules apply here. First one, the direction of the tangent to a magnetic field line at any point gives the direction of magnetic field at that point. And the spacing of the lines represent the magnitude of magnetic field. The magnetic field is stronger uh, where the lines are close together, and it's weaker where the lines are far apart. So in this figure, here is a magnetic field near a bar magnet, and magnetic field lines are represented here. The lines pass through the magnet and they form closed loops, which are not shown here. And the external magnetic effects of a bar magnet are stronger near its ends, where the field lines are mostly closely spaced. The magnetic field of the bar magnet collects the iron filling when we sprinkle iron filling near the bar magnet. It collects fillings nearly the two ends of the magnet. Then there are the closed field lines enter one end of a magnet and exit the other end. The end of a magnet from which the field line emerge is called the north pole of the magnet, and the end where the field lines enter the magnet is called the south pole. Because a magnet has two poles, so it is said to be a magnetic dipole. And the magnets we mostly use to fix nodes on refrigerators are kind of short bar magnets. So here magnetic field lines produced by several common sources of magnetic field are shown. A horseshoe magnet and a magnet that has bent around into a shape of a C, so that the north and south poles face each other. So in the gap between the poles of the magnet, the field lines are approximately straight and equally spaced. It shows that the magnetic field in this region is approximately uniform. Then this is magnetic field lines of a current carrying wire, and here this is the magnetic field of a current carrying loop. And because these magnetic field patterns are three-dimensional, so it's necessary to draw magnetic field lines that point into or out of the plane of a drawing. So to do this, we use a dot to represent a vector directed out of the plane, and a cross to represent a vector directed into the plane. So there is a good way to remember these conventions. We can think of a dot as the head of an arrow coming directly towards you, and you can also think of a cross as the feather of an arrow flying directly away from you. So now let's discuss the concept of magnetic flux and Gauss's law for magnetism. We can define magnetic flux through a surface just as we defined electric flux, and we can relate electric flux with Gauss's law, so we can do the same here. For this we can take a surface, and we can divide surface into elements of area dA, and for each element we determine the B or component of magnetic field normal to the surface at the position of that element. So from this figure we can guess that the perpendicular component is phi is the angle between the direction of B and a line perpendicular to the surface. So this component varies from point to point on the surface. We can define the magnetic flux through this area as this small area. So the total magnetic flux through the surface is the sum of the contributions from the individual area elements, and then we will use integration. Magnetic flux through a surface. And if you carefully look into this expression, it will remind you about the concept of the area vector and the surface integral that we previously studied in electrostatics. So magnetic flux is a scalar quantity, and in a special case in which B is uniform over a plane surface with total area A, B and B perpendicular and phi are the same at all points on the surface. In such condition, this phi B becomes due to A and this becomes B cos phi. So if B perpendicular to the surface, then cos phi becomes 1 and this equation reduces to B into A. This concept of magnetic flux is very useful in this magnetism, and in the next chapters we are going to study this magnetic flux extensively, especially in our study of electromagnetic inductions. The unit of magnetic flux is equal to the unit of magnetic field times the unit of area. So, and it is Weber. The unit is called Weber. So 1 Weber is equal to 1 into meter square, and we know 1 Tesla is equal to 1 Newton per ampere, so we can convert this into 1 Newton meter per ampere. Other thing is in Gauss's law, we knew that the total electric flux through a closed surface is proportional to the total charge enclosed by the surface. Total electric flux is proportional to the total charge enclosed. And let's apply the same rule here. If the closed surface encloses an electric dipole, then the total electric flux will be 0 because the total charge is 0. By analogy, if we apply the same thing for a magnet, then there is no such magnetic monopole or a single charge here. So the total magnetic flux through a closed surface would be proportional to the total magnetic charge enclosed. And here we know that there is a dipole. So based on this analogy, there is a magnetic dipole. So based on this analogy, we can say that the total magnetic flux through a closed surface is 0. Closed surface B dot dA is 0. This equation is sometimes called as Gauss's law for magnetism. And if in these figures, like here, if you draw a closed surface anywhere in any of the field maps, then you will see that every field line that enters the surface also exits from it, and the net flux through the surface is 0. So it follows that magnetic field lines always form closed loops. Okay, now let's